Okay, can everybody see my screen okay? And hear me okay? Right. First of all, I must apologise. I'm having to use Internet Explorer now today for this because my Firefox is playing it, but won't worry about too much. Right, what I'm going to do today is hopefully give an understandable introduction to this new thing, MIMO technology and 11N technology. I'm sure I shall probably cover some things which people are fully aware of, but please bear with me because I don't quite know the competence of everybody that's going to be listening. So let's start from the beginning. Next slide. How do you do the next slide on this? Okay, just a bit of background really. You understand that so far we've had the 11B technology, which is the old 11 meg stuff, using CMSA media access, which in practice only gave a true throughput of sort of 5.9 to 7.1, depending on whether you're using TCP or UDP. Then we have the 11G, yet again also using the 2.4 gig ISM band, that's the free-for-all band. This now increased the speeds up to a backbone fire rate of 54 meg, which in practice gives a true throughput of near the sort of mid-20s. And this one actually started using OFDM technology for transmitting the signals. You don't necessarily have to understand what that means, but it was just a way of breaking up the signal into sort of one big channel sending data, send it into a number of small channels sending data, which made it more reliable. At the same time, there was also the 11A standard, which was very similar to 11G. It uses the OFDM of 11G, but this was in the 5 gigahertz uniband, which is the sort of generic region that goes from about 5.1 up to about 5.8 gig, but that is actually split in 3 sections just to make it more complicated. This had various advantages over the old 11G in that it used OFDM over the complete bandwidth. The OFDM for the 11G only kicked in when speeds were greater than 20 meg, which was a bit of a catch-22 situation really, because you wanted the OFDM for better reliability, but it only kicked in when you actually had good reliability at speeds greater than 20 meg. A bit of a waste of time really, but the OFDM for 11A kicks in at all the speeds. And then in the last year or so we've had the new kid on the block, the 11N. Now the 11N is not defined to any particular band. You can get 11N products for the 2.4 or the 5 gig bands. It still has the 11G legacy support, so you can still run your 11G equipment with 11N equipment, but it starts to have some new tweaks on it, which it has this MIMO, which is multiple in, multiple out, which enables you to run multiple streams. It uses wider data channels and has improved extensions for how it actually sends the data. So the way it actually transmits the data has been improved, which has produced an improvement in net throughput. And in theory, the 11N allows us to go to a maximum of a 600 meg backbone fire rate, which comes out to a real theoretical data throughput of over 200 meg. Though I haven't seen any 11 equipment yet that's actually given anything beyond a real data throughput of about 80 meg. Let's go to the next screen. So just to summarize that, as you can see here, we've got the 4 standards. You can see these are the maximum 5 data rates, typical data throughput, operating frequency bands, and the maximum number of channels. And this is important. Now the 2.4 gig region using 20 meg channels, you tend to find that there's only about 3 non-overlapping 20 meg channels in the 2.4 gig region. Now the 11A using 5 gig has access to a considerably wider band, and it actually has access to, in the whole band, access to 24 20 meg channels, or 12 meg 40 meg channels. Now what in practice this means is the 11N, which yet again, as I say, reminds you, needs to use 40 meg channels to work properly, really you can only get one 11N connection working in the 2.4 gig, or you can get up to about 12 working in the 5 gig. This is if you want to make maximum advantage of all the 11N capabilities. Now, I've got to apologise for this. Some people may think it's grandmother suck eggs type example here, but what I'm trying to do here is I'm trying to give a background of exactly what a wave looks like. Now my example here is a common example used by everybody who wants to explain what waves are. You drop a stone in a pool and you get waves radiating out. And here we've got a series of diagrams that I've nicked from someone's website, and you can see how the stone hits the water, and then you have a series of waves on the water coming out from the source point. And this is exactly the principle that Wi-Fi is. Your source point in this Wi-Fi will be your aerial stuck up in the air, and what it's doing is it's radiating RF waves outward from that point. And if you've got an omni antenna, that's a 360-degree transmission antenna, then it'll look pretty similar. If you could see RF waves, it would look pretty similar to the pond illustration. So you've got the waves cycling out, circling out from the actual source point. Now, if you've got waves of RF coming out from a source point, let's say you've got 2 RF waves coming out from your source point, then if you imagine you've got wave number 1, wave number 2. Now, if this is your receiver here, the way these waves are received by the receiver is important. Now, if the 2 waves are both synchronized like this, so you can see the peaks are both in synchronization and the troughs are both in synchronization, then what happens is these 2 waves add together, which is the example you see here. You end up with a resultant wave which is twice the size, or the combined size, of the 2 individual waves. Now, let's go to the opposite extreme though. The opposite extreme is that your second wave is actually exactly out of phase. What that means is that the peaks of the first wave actually align with the troughs of the second wave. Now the effect now is that when you add these 2 together, what you actually end up with is no wave. Now this just goes to illustrate the importance of what phase is. This is this ability to actually line up the signals. Very important when you're transmitting RF stuff. And it's this problem, or the way the phases work and add together, which is one of the main criteria that decides how well radio waves or RF or Wi-Fi actually goes through a building or around a building. Because when waves go round inside a building, what's happening is the waves are hitting and reflecting off the walls. So if you imagine you've got 2 radio waves emitting from your source, and one just happens to go by a route which only hits, let's say, 2 walls, and one goes by a route which hits 3 walls, then the one that's gone by 3 walls is going to take slightly longer, or potentially slightly longer, to get there than the one that's gone by reflecting off 2 walls. Which means when they arrive at the destination, they're no longer going to be in phase. They were transmitted in phase, but when they arrive at the other end, they're not. Now, this characteristic is what is called multipath effects. Now, in 11G, 11B networking, the multipath effects is one of the big problems with trying to get Wi-Fi to build or transmit within a property. The problem is the waves arriving out of sync, which means the resultant wave is distorted at the very least, but at the worst, obviously, it could be nothing. So 11N actually tries to take this a stage further, and rather than the phase difference hurting 11N, what 11N does is it uses that phase difference to its advantage. It uses the fact that it can tell the difference between this wave and this wave by the phase difference. So whereas with 11G, that causes problems, with 11N, it uses that to its advantage. Let's go back to the next slide. Right. Now, just to take this to the extreme, let's imagine you've got a 2 aerial source. Now, each aerial is sending out radial waves. So you can see the radial waves from this antenna and the ones from this antenna. And what we've got here is we've got the peaks and the troughs for each wave. So this is looking down on the top. So you can imagine the wave is going trough, peak, trough, peak, trough, peak, radiating upwards. And the same for here. And you can see where the waves actually hit each other. At some points they're hitting each other in phase, in which case you get a higher wave, and at some